Okay, here's just a quick video about these free body diagrams that are on the top of this third page of the lab. So we're looking at, for the friction lab, when you start pulling immediately before it starts moving, when the block begins to move, and when the block's moving at a constant velocity. Basically for this A, B, C, D, here's what we're looking at is on this graph, and I just made up some numbers here that would work, at least for the purpose of showing you how this works. Part A, when you start pulling, that's looking at just some random location that's along this increase. So I'm just going to label that point A. Immediately before it starts moving, so I'm looking at the breakaway point. So that's the breakaway point there, is before it starts moving. As it starts moving, so just immediately as it begins to move, that's going to be like right here, basically. So that's point C. Because what happened is the kinetic friction from point B, the kinetic friction immediately jumps down. And the kinetic friction is there. So there's our force of friction kinetic. But our blue line that I have here, that's the tension force. So that's the tension from our string that's pulling it. So for just a moment, the tension is up here, but the kinetic friction is down here. So the kinetic friction jumped. And then kinetic friction stays the same the whole time. But the tension doesn't immediately jump. The tension has to kind of slack off for a moment. So part C is immediately after, I'll call it breakaway point. I'll just do that abbreviation. And then when it's at a constant velocity, so just sometime over here, that's going to be that part D for these free body diagrams. All right, so immediately as we start to pull, well, there's gravity and there's normal force. So force of gravity goes straight down, normal force goes straight up. Please be careful that your force of gravity and your normal force, that the arrow points are exactly at the same level, because we're not accelerating up and down, so they must be exactly the same length. Our force of friction, well, it's just up here, so we don't have too much tension or too much tension yet, right? Because this is our applied force. This is our tension force, which is in that newtons as it's labeled there. So our tension force, we don't have much yet. So I'll go, well, let's go 1.5 boxes. There's our tension. And it's when I start pulling, but we haven't started moving yet. So since we haven't started moving, acceleration is 0, so our force of friction must be exactly the same, must be 1.5 boxes. So this is force of friction, and I'll call it static because we haven't started sliding. Part B, immediately before it starts moving. Okay, so before moving, we're still on static, but now we're at the breakaway point. So we'll have static friction maximum. Well, gravity goes down, normal force goes up, and they're the exact same magnitudes as they were because mass didn't change, gravity didn't change for this trial of this block. So since those all didn't change, those two forces stay the same, but our tension force has now increased. I'm going to go to 3. So our tension force is now increased, and it's tempting to go to 4. But before it starts moving, well, our acceleration is still equal to 0 in both of our axes. But that also applies to the x-axis. And force of friction static maximum is what happens at the breakaway point. But remember that force of friction, because mu is less than 1, and right, we have our force of friction is mu times normal force. And this is for static friction maximum or for kinetic friction. That means that force of friction, because this is less than 1, must be less than normal force always. That must always be true. So our force of friction static maximum must be smaller than our normal force. So that's why it's important that this is 3 boxes, this is 4 boxes. We cannot do all 4 boxes for our friction because friction must be less than normal force. When the block begins to move, okay, so begins to move, that's this moment right here. where we said, okay, now it's moving, so our kinetic friction has jumped down. So we've jumped down to our smaller kinetic friction. Well, first, I guess we'll do the force of gravity and our normal force. Again, they haven't changed, so they're the same from trial to trial. Our kinetic friction, because now we're at kinetic, so it must be less than our static friction max. So I'll go 2 boxes. Since our static max was 3, our kinetic force of friction, kinetic, will be 2. And I just used the green pen here because that's how we modeled it up here, is with the green pen. But our tension force is still pretty much exactly what it was during that breakaway point. So our tension should still be the same as it was previous. So I'm going to do those 3 boxes again, tension force. And then this last one. Before we do the last, we can see that acceleration is greater than 0 because our rightward forces will win out over our leftward forces. And that's how we go from rest to moving. But now at the end, now we have a constant velocity, so we're back to our acceleration is 0. All right, same gravity, same normal force, Our kinetic friction never changes. So kinetic friction, this is another big takeaway. Force of friction, kinetic, never changes. Because when we look at the equation for it, it is kinetic friction equals mu k times Fn. Mu k, that's defined by the surfaces. So if the surfaces don't change, then mu doesn't change. And then normal force, right, it doesn't change ever because our gravitational force doesn't change. So our force of friction cannot change once we're in kinetic. So since I gave us 2 boxes, I committed to 2 boxes here for our kinetic force of friction. Force of friction, kinetic. But now we're at a constant velocity, so acceleration 0. Therefore, our forward force, our tension force, must be the same as our backward. So since our backward friction force is 2 boxes, our tension force must now be 2 boxes. So there's a brief overview on how to do those free body diagrams. Please reach out if you have any questions.